Hello, my name is Wei Kang, and this interview of oral history is a part of the joint effort of IEEE History Center and SAM CT 15. It's my great pleasure to introduce Professor Art Krener of U.S. Naval Postgraduate School and the University of California at Davis. Welcome to the interview, Art.
Thank you, Wei.
About 2 weeks ago, I just saw the news that you just won the IEEE Control System Award, a very prestigious award and well-reserved, of course. Congratulations.
Well, thank you.
So why don't we start from some kind of a background information, where were you brought up and where did you begin your university studies?
Well, I was born during the Second World War in Brooklyn, New York. My father was off fighting the war, and I lived with, as a baby, I lived with my aunt and my mother and my grandmother in a big extended household. And when he came back from the war, he joined the New York City Police Department. And we lived together in a second house as a big extended family for a while. But then when I was 8 years old, my family moved to Queens, from Brooklyn to Queens. And we lived, my brother, my mother and father and myself lived as a nuclear family. So it was a working class. They didn't overpay policemen in those days. I don't think they still do today. And my mother was a school secretary. So I went to local parochial schools, Catholic schools. Then I went to the Jesuit High School in Brooklyn. Had to take the subway an hour each way every day to get to the school. And very often I was late, so I had to spend an extra half hour after school in jug, as the priest called it. Then I went on to Holy Cross College in Worcester, Massachusetts, another Jesuit institution. All the time I wanted to be a math major, but I had no idea what control theory was, and it just wasn't on my horizon.
Your college, what was your major in college? Mathematics?
I majored in math. I had been interested in chemistry and physics in high school, but then I looked at the schedule in Holy Cross in those days. Your four-year schedule was completely planned out except for one or two electives. And I thought that math had more electives than physics and chemistry. If I were in physics and chemistry, I would have been in the labs a lot more. And I had no desire to do that. So I majored in math. And then in 1964, I graduated. And I applied to several graduate schools. I really wanted to go to Berkeley. And I heard acceptances from many schools, but never heard from Berkeley. So I went up to one of the professors in the math department there, who had just come back from a sabbatical at Berkeley, and told him my situation, and he made a phone call or two, and the next day I had a TA-ship offer. So in the fall of 1964, I moved from Worcester, Massachusetts to Berkeley, California.
I see. So it seems that you actually start very early, get interested in mathematics already.
Oh yeah, I had always been easy. Math always came easy for me.
And under whose direction did you work in Berkeley?
Well, that's a complicated story too. I arrived in the fall of 1964 during the free speech movement, which was the first of the disturbances in Berkeley during the 60s. And there were 400 graduate students at Berkeley in mathematics in those days, and about 70 or 80 professors. So to say you got personal attention would be a gross exaggeration. I spent the first 2 years taking courses. I had to do a lot of adjusting in my study habits because I had always breezed through undergraduate mathematics courses, and all of a sudden the competition was a lot harder and fiercer at Berkeley. But I passed my qualifying exams the second year, and then looked around for a thesis advisor, and I was TAing a course in numerical analysis for a fellow named Sherman Lehman. And we got to talking, and I was taking a course in linear programming over in mechanical engineering. And I expressed my interest in the material, and he said that he had been a postdoc with Richard Bellman in the 50s at the Rand Institute, and they had worked on a infinite time version of linear programming. They called it continuous linear programming. Basically, the linear operators are linear integral operators. So they had found that, well, if you froze one of these continuous linear programs at a fixed time, it was a classical linear program. And what they had found by a series of examples was that the optimal trajectories jumped from one extreme point to the other as the feasible set rotated as time marched. As time marched, the feasible set of the optimal control problem changed, but the optimal solution jumped from one trajectory to the other. And they had never been able to prove that this was a universal phenomenon, so that was my first thesis problem.
Mm-hmm. Then you mentioned that's kind of complicated. It so far sounds like kind of a normal.
Yeah, I was making normal progress.
Yeah.
And then Sherman Wayman, my advisor, was hit in a terrible car accident. Somebody ran a red light and smashed into him. And he was very seriously ill and not functioning mathematically for about a year afterwards. And I kind of floated with these 400 graduate students and 80 faculty. Nobody was tracking anybody very well. So I floated for a while, kept on coming back, taking courses in functional analysis because I thought the solution to my problem was a problem in functional analysis, some kind of Hahn-Banach theorem or something like that. And then after about 2 or 3 years, I started to doubt that. Lehman came back, but he wasn't really fully functional. And then he had a stroke, and the same thing happened. So I was kind of adrift. I had a problem. I thought I had techniques, functional analysis techniques, but I couldn't drive anything home. So I had taken a course in differential geometry from S.S. Chern, the famous Chinese-American geometer. And Chern had taught me what the Lie bracket was in a very fundamental, intuitive way. He was a brilliant speaker and a very kind man. So I kind of formulated what I was working on in some kind of geometric terms and went to him and explained to him what I was working on. He said to me, I don't know the answer to the question you're asking, but I think I know who might know it. And he sent me to the physics department where Bob Herman was a visiting professor. Now, for people that don't know Bob, he was a flamboyant mathematician, Princeton graduate, man of immense scope, but very little discipline. He had more ideas than he could ever carry through. And so anyhow, Bob listened to my question and said, "Oh, you're looking for Chalice Theorem." The Chalice Theorem is a theorem by a Chinese mathematician who proved it in Shanghai while the Japanese were bombing him. And it turned out I was looking for a unidirectional version of Chalice Theorem. Chalice Theorem allows trajectories to go backwards and forwards, but in controlled time marches in only one direction. So anyhow, I was much encouraged. I had a faithful sidekick, my German Shepherd dog, who followed me around campus. And when I went into Bob's office the first time, he chain smoked cigars in those days, and the whole room was just full of cigars. And so between him and his cigars and me and my dog, we were a bunch of odd couples. So
this is Berkeley.
It was Berkeley. It was definitely Berkeley. And of course, there were a series of disturbances in Berkeley: People's Park, free speech, Third World. I got interested in student politics. I was the shop steward for the math department TA union, and got arrested one day and released 2 hours later. They were just harassing us. But it was an exciting time. And then I met my wife-to-be, and I realized that I had wasted a lot of time enjoying the distractions of Berkeley. So I knuckled down and said, well, I've got to find a second thesis advisor. So the only other guy in the math department that knew anything about optimal control or control in general was a man named Stephen Diliberto. He was a student of Solomon Lefschetz and had written a paper or two on the Pontryagin maximum principle. So I went to see him and I explained to him what I was trying to work on, and by that time I knew what I was trying to do was a bang-bang theorem in optimal control. So if there's an optimal solution, there's a bang-bang optimal solution. This information was conveyed to me by one of my fellow graduate students, and that really marks my transition as becoming a control theorist. That's the first time I realized I was doing control. So anyhow, I explained to Diliberto what I was working on and asked would he mind taking me on as a student. And so we started meeting every week. But unfortunately, Diliberto was going through a divorce. So he didn't show up every week. He showed up every other week. And I was getting desperate. Finally, I said to him, how much more do I have to do to get out of here, get out of graduate school? And he said to me, write it up. And so, of course, in the process of writing it up, I realized a lot of things that I thought were obvious and true were not obvious and not true. And after several false starts, I finally managed to produce a PhD. And I graduated in 1971. And one of the nice things Diliberto did for me was to write 100 letters. Now, this is impressive in those days because this was before word processors. So he had a secretary type 100 letters of recommendation and cold send them out. And one of them landed on the desk of Roger Brockett at Harvard. And Roger had also been interacting with Bob Herman and had come to the same conclusion that Bob and I had come to, which was that Lee Brackett had a lot to contribute to nonlinear control. So he called me up and we chatted a little bit, and I had a family wedding in New York at the time, so I agreed to go up and meet with him, and we had a very nice chat. And then he said, keep in touch, and we'll see what happens. So I was able to grab one of the last tenure-track jobs of the early 70s. The job market was very generous in the 60s, late 60s, but by 1971, 72, it was really drying up.
So I don't mean to interrupt. So basically, when you were at Berkeley as a graduate student, you already made up your mind about being a professor in university rather than going to industry. So you have this clear career plan.
No. Yeah, I've always wanted to be a mathematician, an academic mathematician. So fortunately, UC Davis, 70 miles away from Berkeley, made me a job offer, and I snapped it up, and in the fall of 71 I started at Davis. And I was at Davis for 35 years until I retired in 2006. But along the way, Roger Brockett invited me to come back to Harvard as a postdoctoral fellow. Now, I was already in a tenure-track position, so I wasn't about to resign the tenure-track position. So I just told my university I was taking a leave of absence to work at Harvard. Roger represented me as a postdoctoral fellow to the Harvard administration, and I got time on the tenure clock for my year in Harvard in 74, 75. And that had a profound influence on me. Roger is a remarkable person, very generous, very enthusiastic, a deep thinker, and so he really supplied a lot of the education, the training that I didn't get as a graduate student.
So you spent 35 years in Davis, and I know that you visited many other places and universities for your sabbatical leaves and projects. So where else have you worked and visited?
In 1973, there was a famous meeting in geometric control theory, nonlinear geometric control theory, organized by Roger Brockett and David Main in London. And I met Alberto Isidori there, who became a very close friend and collaborator over the years. A couple years later, I visited Italy, And Alberto said, would you care to come for a longer period? And I was just going through a divorce by that time, so I was very flexible. And I said, sure. So that was my first big trip away from home besides Harvard, was 3 months that I spent with Alberto in Rome in 1979.
I see. Yeah, go ahead.
And we had a very successful collaboration. We were able to produce a paper that won the Best Paper Award in the IEEE Journal.
And yeah, I certainly heard a lot about this London workshop. And
oh yeah.
It's so from Harvard, the London workshop, and the Rome. That is all. During this period of time, you were most focusing on the geometric controller.
Almost completely. Mm-hmm. And you know, frankly, by 1979, early 1978, 76, some of the fundamental questions of reachability had been dealt with by geometric methods. And so the field was getting a little stale, and there were several new impetuses. One is my collaboration with Alberto that really opened up a broader horizon. So Alberto had a very clear image, a very clear goal of taking to nonlinear systems many of the geometric concepts of linear systems. And I think he particularly looked to the work of Wonum and Morse, and that's what we worked on when we were there. And then, of course, later he and Chris Burns generalized Wonum and Bruce Francis in their famous papers on nonlinear regulation.
Mm-hmm. And I remember that in 80s, you spent a few years kind of away from the geometric control, working on reciprocal process.
Oh, yeah.
Anything you want to talk about?
Well, frankly, I think it's the best work I ever did. Wow. But it's completely ignored. it hasn't raised a blip. In about 1980 or so, I attended a workshop at the Naval Postgraduate School on mathematical problems in image processing. And the dominant theme of that meeting was to generalize Kalman filtering from one dimension to two dimensions. When I say dimensions, I mean independent variables, time, so two-dimensional time. And so people were doing Kalman filtering for partial difference models that would be called first-order hyperbolic or parabolic. And so they had some kind of causality where the information structure in the process would process, say, from upper left down to lower right in hyperbolic and line by line in parabolic scanning. I thought many of the fundamental questions had not been addressed in this field. So I said to myself, well, you know, the most significant thing about second order or first and second order partial difference equations is this characteristic structure of the equations. Whether there are characteristics and how many of them are they real and so on. So the question I asked many people at that conference was, how does the interplay between the characteristic structure and the stochastic structure work itself out? So how can you tell from, say, the covariance of the process, this two-dimensional process on a two-dimensional n vector over a two-dimensional domain, how could you deduce what kind of differential equation or difference equation it came from? And surprisingly, nobody had thought to ask that question. So I said, well, you know, there's a fun question. I'll just knock it off in a weekend. Well, I started doing it. It was a long weekend. It was. So I said, well, you know, maybe what I should do is back up. You know, I always tell my graduate students, Wei was my graduate student. I always tell my graduate students, always attack the simplest problem that you don't understand. Don't try to do the general problem right away. Just get your feet on the lowest rung of the ladder and work your way up. So I said, well, let's take a standard one-dimensional process, A, B, C, D model, and instead of putting initial conditions on the process, let's put boundary conditions. So let's, of the x0, x at time 0 and x at time t, there's 2n degrees of freedom there. Let's constrain those 2n degrees of freedom to be a Gaussian random variable, an n-dimensional, some n linear functionals of those 2n degrees of freedom to be an n-dimensional Gaussian random variable. You have to worry about whether the process is well posed, but that's a fairly straightforward question. So I got these boundary value models, which I was very happy with, and did a lot of work in classifying stationary 1- and 2-dimensional boundary value models. But I could never get my hand on the stochastic characterization of these models. If initial conditions were on the process, then it was a Markov process. But boundary conditions destroyed the Markovian property. What was the stochastic replacement for that? So I stumbled on a paper of Gene Wang that mentioned reciprocal processes, and he referenced a paper by a guy named Benton Jameson. And so Jameson's paper that I found claimed to have classified all one-dimensional stationary reciprocal processes. Stationary in the sense of the covariance is a function of t minus s rather than t and s. So I compared his list with the list that I had worked out for the boundary value processes, and there were considerable overlap, but each list had one that the other one didn't have. So I was very frustrated. I didn't know what to make of this. And about a year later, I woke up one morning, you know how serendipity sometimes hits. I woke up one morning with a proof in my head that all these boundary value processes were actually reciprocal processes. So I went back to the literature and did a forward search from Jameson's article and found that there had been 2 corrections of Jameson's list, 2 additions, and when you took the full list, the augmented list, my set was a subset of Jameson. So I knew that every boundary value process was a reciprocal process. And then what about the one additional process that wasn't from a boundary value process? And so that led me into reciprocal processes, stochastic differential equations of second order. The Fokker-Planck equation for these equations is replaced by a series of conservation laws, very similar to the conservation laws of classical mechanics. And it's a beautiful theory. And then I discovered later that the whole idea of reciprocal dates back to the Russian mathematician, what's his name? Serge Bernstein, who was trying to formalize some ideas of Feynman. Feynman had been trying to stochastize quantum mechanics, make it into a stochastic model driven by white noise of some sort or other. And he had some pin processes. He had a vague paper about pinning processes. And so Bernstein gave the rigorous definition that if you have a process parameter by its one dimension, what happens in between the any 2 times is independent of what happens outside the 2 times, conditioned on the value of the process. Now it turns out every Markov process is reciprocal, but not vice versa. So this got me off on reciprocal processes, and we thought we had achieved at one point Schrödinger's goal of stochastizing quantum mechanics, but that was only in the ground state of the quantum harmonic oscillator. Once we went to the first excited state, it all fell apart. So, but it was fun.
Wow. And along these, so far you mentioned the many collaborators, from Alberto Stidori to Roger Brackett, and so I know that you have a very impressive list of collaborators, and some collaboration led to award-winning work. And so tell us about some of your close collaborators.
Well, I was very fortunate, and I think this is a characteristic that I found in the controls community, that people are very open, very accepting, very generous, and not competitive, not excessively competitive. Everybody wants to do well. But so I've collaborated several times with people in papers, Isidori. I worked with some graduate students on the reciprocal processes. Bernard Levy in the electrical engineering department at Davis also collaborated on reciprocal processes. He made some fundamental insights. Then later on, I got into power series methods and worked with Mont Hubbard in the mechanical engineering department at Davis. But Chris Burns was a big influence on me. His work with Isidori opened my eyes. So it's not just people that you collaborate with, it's people who work near you whose work really impresses you. And there was a lot of them.
Yeah, so talking about the people near you, they have, their influence and, collaboration, everything. So who do you think has had the most profound effect on your career and why?
Well, I mean, there's 2 or 3 choices here. I think Roger Brockett would be the first really seminal figure in my career. And then Alberto Isidori would be the second one, seminal figure in my career. You contributed a lot.
Oh, that's my honor. Thank you.
So, yeah, those were the names that come off the top of my head.
Then, for like you're 45 or more, probably, depending on the graduate school or not, but your career for all these 45 years, there are, of course, exciting moments, not so exciting moments, and so on. So what do you consider to be the highlights of your career?
Well, getting out of graduate school was after being on the edge of failure for 7 years, getting out and getting a job was a very important thing. Working with Roger. Bob Herman had a major influence, but in both positive and negative sense. Bob would start projects but never finish them. So he'd have great ideas, and if you just listened to him, you could mine his ideas. So the paper Bob and I wrote on nonlinear controllability and observability. It was initially his idea, but I put all the work into it, so that was great. Getting tenure. I mean, I got tenure, and the 70s were not kind to academics. There were not a whole lot of jobs. The baby boomers had all left. And the 60s, all the new universities had filled up their ranks of their faculty. So that was a brief thing. So that was, things stagnate for a while, and then you get a new idea, you get a new direction, and you take off with that.
Yeah, I heard that during the early 70s, late 60s, the job market was very hard, but you are lucky to have a professor wrote 100 letters for you.
Yeah.
So, that's maybe that's related. You have a good time, bad time. Now we talk about the highlights. How about the challenges? Any challenges you feel?
I mean, I pounded my head against theorems for many days sometimes. I'm very stubborn, and maybe sometimes too stubborn, and I don't see that what I'm trying to prove couldn't possibly be true until several months or weeks of it. But I did have a rough spot in my 50s, in my early 50s. I went through a bout of depression. I had developed an allergic reaction to alcohol and to fruit juice, and I was getting migraine headaches almost every day.
Wow.
And so this led to depression, divorce. So, I suffered, but I survived.
Yeah. So let's maybe come back a little bit to the topics. I noticed that we mentioned the geometric control. Of course, that's how that topic attracted me to get into the field actually in the first place, and later reciprocal process. I know that you also had some work on software packages even, that's kind of a very different from your theoretical work in terms of style, right?
Yeah, I've become a born-again Christian, if you'll excuse the phrase, for computation. I think too much, even at a meeting like this, too much of the papers that are presented have no hope of ever being computable. And I think our discipline needs to be more informed about choices of problems that will have computable outcomes. They're not necessarily immediately. I'm not a Neanderthal about it. But eventually, everything that we do should be computable and should become a tool for the broader community. I mean, as mathematicians, we are tool creators in control, and we make very specialized tools that may not, and we may do calculations based on those tools, but these tools are not easily transferred into mass production. And the counterexample to what I'm saying here is what MATLAB has done for linear systems theory. It has completely revolutionized LQR, Kalman filtering, and so on, by making relatively easy, stable, widely discernible packages to do fundamental control. So I think a larger proportion of our community, and I mean the nonlinear community here, not so much the linear community, a larger proportion of the nonlinear community needs to devote more effort into making mass-produced tools, ones that you can ship out the door and your neighbor down the block can use it with a minimum of help.
So these work, I know that, these control theory is somewhere like in between mathematics and engineering, so it's kind of, you can go to applied side and pure theoretical side. And then I know that your work was funded by different agencies. So anything you can tell us about your funding situation for the last, or sponsors?
Well, I think I was very lucky with funding. I got my first NSF grant 2 or 3 years after I arrived at Davis, and basically have been with funding ever since. Not a lot of funding. I've never been comfortable. I mean, this is the difference between my style and the style of many engineering professors. And I'm not putting their style down, but I'm just saying it's not my style. My style is to work relatively alone or with 1 or 2 graduate students, a low budget, relatively stable funding, so that you don't have the headache of waking up next morning and saying, I just lost my grant, I've got 5 postdocs whose mouth I have to feed. I mean, that, I've never been, I'm risk averse that way. Now, I have great respect for the people in our field that have really generated steady streams of outstanding graduate students, and I'll mention a few of them. Roger Brockett in the 70s and 80s particularly, but throughout his career, generated a large number of very successful graduate students. Almost everybody of my age, plus or minus 5, who is a nonlinear systems theorist, was touched in some way by Roger. And then after Roger, Shankar Shastri, who's moved on to administrative responsibilities. But Shankar invited me to give a graduate course on nonlinear systems in Berkeley in the mid-'80s. And he had assembled, with his enthusiasm and his mixture of machines and mathematics, he had assembled and mobilized a whole group of very talented people. Andy Teal, Richard Murray, Dawn Tilbury, the list goes on, and they're just fantastic. Peter Kirkotovich is another guy who generated a tremendous stream of really outstanding graduate students. over the years. Peter did it over a longer period of time, maybe not so intense at any one time. But I mean, I think of Igor Mesic. But he wasn't one of Peter's graduate students, but he was a protege of, of Peter. And then Miroslav Kristic. But the list, I've apologized to people whose names I can't recall right off the top of my head. So that, I think, that style of business, doing business, is in some ways the lifeblood of the discipline. And I think Jacques-Louis Lyon falls into that category. But it wasn't my style, so I tended to stay away from it. A few good men is what I was looking for.
Okay, now a lot of the serious topics. Let's go to something like, for example, do you have any anecdotes or stories you want to share for during whatever?
You should have brought a bottle of wine. I don't think I want to say anything.
Okay. Yeah. So we talked a lot about past, your 40-some years career, and now let's talk a little bit about now and the future. So currently, what control areas do you find exciting?
Well, I think the field has really changed, and if I were giving advice to a young person coming into the field, I think the role of theoreticians like myself has been greatly diminished. We have attacked and solved a lot of the fundamental problems in nonlinear and linear systems. So we don't need to produce a lot of theorists in those areas. What we need to do is have people carry the message from our discipline to other disciplines. And so I'm very encouraged by seeing people in going into mathematical biology. Systems biology is basically set up for our talents. As soon as we learn a few chemistry and biology. Big data set up for our talents. Control of large, complicated structures like electricity distribution systems. These are all topics that are made for our skill set, and I'm very encouraged to see people going into that. And again, come back to computation. I think those people that want to stay as theorists have a responsibility to produce usable tools for other people. If you're going to just produce a theory that doesn't go anywhere, then I think there really isn't a whole lot of need for that. What we need is a software package like the control systems toolbox for nonlinear systems.
Yeah, you kind of already touched that topic, but anyway, to any field, including control area, attracting young, talented people is always very important.
Right.
So specifically, what advice would you give to young people thinking about a career in control field?
Well, think fundamental. The more fundamental that you can think of, the better off you are. Don't be afraid of hard work. I spent, I don't know how many years at Berkeley trying to prove that bang-bang theorem, and it wasn't true. But I went through reams of paper. I would go to the computer. In those days, they had batch processing of computer programs, and there'd be these stacks of paper, and I would grab a stack and take it home and fill them all up on the back with that. So hard work. There's no easy road to success. What else would I say? Well, choose your problem and the people that you associate with very carefully, because I think at a certain level of the people in, most of the people in this room, in this conference, there is a basic fundamental set of skills that almost all of us have, and we all have them pretty much to the same degree. So what separates people out is their shot selection. Choosing a interesting fundamental problem to work on and then sticking with it I think that would be the best advice I could give anybody. Particularly, I mean, anybody that's mathematically oriented. If you're engineeringly oriented, then there's other advice, but I don't want to give that advice because I'm not an engineer.
Okay, so I think it's been an honor and a great pleasure talking to you. You provide a lot of very valuable, insights and a view about important issues of a control area. And thank you very much.
Thank you, Wei.